All right, team, let's jump right in. Today, we are walking through a truly massive capability milestone for our architecture. We're talking about the successful, mathematically sound integration of the Sexos host controller pipeline directly into the Sexos microkernel. As fellow engineers building a pure single-address space OS, you all know exactly how critical it is that we nail this driver isolation. So today, we're going to break down exactly how we built a completely lock-free, zero-copy USB data path from bare metal straight to our input subsystem, all while keeping it totally shielded by Intel memory protection keys.
Here is the roadmap for today's review. We'll start with our system invariants, walk through the proven XHCI pipeline, cover the hardware quirks and fixes, look at bounded execution, dive into PDX capability routing, and finally, outline our next work on the Silk UI integration.
Okay, part 1, the law. Let's re-anchor ourselves in our strict system invariants. You all know the drill from our agent_readme first document, but we cannot compromise on these mathematically unrepresentable constraints. We are operating in a pure no-understand Rust environment. That means zero POSIX legacy baggage, absolutely no libc, and no standard threads. We're relying purely on MPK and PKRU isolation to keep our protection domains walled off. How do they talk? PDX IPC only. And remember, cross-protection domain pointers are strictly fundamentally invalid. Oh, and of course, SexDisplay remains the absolute sole writer to the frame buffer. If a piece of USB data can't be routed via a lock-free PDX ring buffer, it simply does not belong in SexOS.
Moving on to Section 2, let's look at the proven XHCI data path we just locked in.
The pipeline we validated flows immutably right across our MPK boundaries. It kicks off at the QEMU XHCI hardware emulation, pushes up to our dedicated SexFA server, which, remember, is operating in its own isolated protection domain. Then, SexFA handles the device enumeration, pulls the descriptors, and does the HID decode. From there, it routes that normalized report over PDX capabilities specifically on slot 9 and terminates cleanly at sexinput. The whole path is proven. We've officially brought up the HID boot mouse.
All right, Section 3, the trenches. Let's talk about the hardware quirks and the register-level fixes we had to hammer out to make this a reality.
As we all know, theory rarely survives actual silicon without putting up a fight. For example, we lost a decent chunk of initial dev time to a sneaky transfer request block, or TRB, type mismatch. Turns out the XHCI command ring uses an entirely different namespace than the transfer ring. We were initially firing off an address device command using type 8. Actually, scratch that. Type 8 on the transfer ring is a transfer no-op. If you look at Section 4.113 of the XHCI 1.2 spec, the command ring strictly requires type 11 for address device and type 13 for evaluate context. Once we fix those constants, the CC/TRB errors completely vanished.
And guys, documenting these lessons is going to save us literal days of debugging down the road. We hit this massive quirk in QEMU's NEC USB XHCI model. We're writing the upper D word first, which the XHCI spec says you should do, caused it to latch as 0 for the internal pointer. Crazy, right? So our resolution was enforcing lower D word first writes for the CRCR and ERDP registers. We also had to implement a reality check for superspeed ports, where the max packet size is heavily enforced at 512, which means we can just acknowledge it and gracefully bypass the evaluate context command. And finally, for control transfers, we had to be incredibly meticulous about preserving critical markers, specifically DW3 bit 6 during setup stages and the IOC, interrupt on completion, bit 5 during status stages.
Section 4. Let's dive into bounded execution and our approach to interrupt in polling.
Within our strict microkernel pipeline, infinite waits are just mathematically unacceptable. Having a driver spin lock on a hardware register is a legacy vulnerability, and we simply do not permit it here. So we've enforced a rigorously bounded execution model across all rings. We're talking bounded loops using yield-based timeouts for USB CMD and USB STS resets. We've fully proved out set configuration on endpoint 0, and we've got endpoint 1 in configured with the proper input control context add flags. Now, for the interrupt in polling, if a transfer event goes missing, we don't just hang the system. No way. It logs a .bad marker and triggers a fatal Parker yield. The system stays alive, and the failing driver domain just yields its time slice.
Moving to Section 5, PDX capability routing, which is really the final handoff in our pipeline.
So how does this actually work in practice?
Our zero-copy, lock-free IPC strategy relies on what we call a minimal capability route, specifically on slot 9. Right at core initialization, the kernel grants SexUSB the hardware-locked permission to talk to sexinput over this single capability domain. SexUSB takes the decoded boot mouse report and blasts it over PDX using type ID 0x260. The payload? It's beautifully simple. Argument 0 holds the button states, and argument 1 is packed with strictly packed integers for our DX, DY, and wheel data. We are exchanging absolutely zero cross-PD pointers here, meaning our invariant against memory leaks is completely preserved.
And finally, Section 6, the frontier, where we're heading next with the Silk UI.
With the capability milestone officially locked in, our immediate next work shifts focus from the hardware boundary up to the user interface boundary. We need sexinput to normalize that raw pointer event, trigger an OP_HID event, and route it straight via PDX to Silk Shell. From there, Silk Shell takes over to prove out our pointer policy and UI rendering, really validating those click, focus, and drag mechanics. And of course, we have to pull all of this off without violating a single one of our established MPK architectural rules.
Ultimately, team, I want you to take a step back and really think about the architectural implications of what we built here. As we bridge this gap into the Silk UI layer, look at the reality of this pipeline. We have entirely decoupled the USB driver from the kernel, we stripped it of any raw pointer access, and we forced every single byte of communication through mathematically verifiable, MPK-isolated PDX channels. Think about how this permanently solves the security and latency flaws we see in legacy monolithic systems. If a malicious USB device tries to exploit a buffer overflow in SexOS, it is literally trapped in a Ring 3 protection domain with zero capability to write to kernel memory. That is the power of a true single address space OS. Let's keep pushing this frontier. Let's get back to the code base, and I'll see you all in the next review.